So today's topic is, it's a small intermediate topic, not related to the previous topic. It's a small. So plastic hinge length. Okay, it's a very small topic. You can see it is what is the plastic hinge length. We will just see it is. Suppose if it is suppose a simply supported beam is there. A vertical load is applied at W at center. You can just take in center. Okay, so just take it as now. See what is the bending moment diagram. How it is bending moment increase? It is a W by 2. It's a W by 2. So bending moment diagram is you already know it's W by 4. Okay, so that's it. So now you have to understand. So one thing you have to maintain. So this course and later RCC design courses, this is applied bending moment. This is applied. So what you applied, it is an applied bending moment. So what is the moment of resistance? It is applied and resistance. You have to understand it is applied and resistance. Resistance is like our capacity. Our capacity depends on section properties. So our capacity is Fy into Z. That is a capacity. Are understood? This is a capacity. This is a applied. If applied moment is higher than the capacity, it is failed. So basically you have to understand. So now you can see it. Now you can see that is applied. You can just delete it. No need of understand. No need of interest. So mostly, not mostly, exactly at center, the highest bending moment is applied. Highest bending moment is applied. Are understood? So if the load is increasing, sir, what is W? No need at all. Just listen it. Okay. If the load is increasing, the applied moment is increasing. It's with the same respect to resistance also increasing. Resistance also increasing. If you apply 10, it will give 10. If you 20, it will give 20. Okay. So now you can understand it's a plastic analysis, not a elastic analysis. Plastic analysis. Okay. So at what moment it will give, it will sustain. It will sustain. What is the moment? It will sustain up to MP. Are understood? Fy into Zp. That's it. In elastic analysis, it will sustain up to this section modulus. It is not plastic section modulus. It will sustain up to at this location up to this load. Are understood? So W is, you can just delete it, W. You can apply the load. It will increase that set at center. It will sustain up to this load. Okay. Load. So that means at the failure, just imagine at the failure, it has a capacity of MP Fy into Z. Fy into Z, na? Z. So suppose I will consider rectangular section. So rectangular section, that is, this is the rectangular section. Okay. So B T. So in rectangular section, what is MP? Rectangular section, what is MP? Or what is MPR? In rectangular section, what is MP? We decide with the where it is, where it be calculated. See it is. So where? So okay. Okay. Second class. So see what is that? MP is what? Fy into BD square by 4. That is the section capacity. Na? Fy, okay, just feel it is. MP is what? Fy BD square by 4. So what is the elastic section? What is the elastic sectional capacity? Fy BD square by 6. We already decided. Okay. So that is Zp and Z. Those are the dependent on Zp, Z. Fy is same. Same material is same. Okay. So now you can see. So MP is Fy BD square by 4. So this is a capacity of capacity. I understood. So this is a capacity of MP Fy BD square by 4. That is a plastic hinge. It reaches to the plastic hinge. It reaches just entered into the plastic hinge. Okay. So now you can feel that if this particular section is reaching the plastic section modulus, that section reaches to the plastic section modulus. This section is 0. This section is applied a moment is 0. There is no resistance. So somewhere I don't know, somewhere the section is reaching to the elastic section modulus. Elastic section modulus means elastic capacity. What is that, sir? Fy BD square by 6 na? It reaches to the full-fledged elastic resistance. I understood. At somewhere it reaches to the full elastic section model, elastic resistance. If the center is reaching to the plastic section modulus, plastic section resistance. I understood. Somewhere I don't know. I understood. This is 0. This is a full-fledged plastic section. It reaches to the full capacity. Full capacity. That's an MP is the full capacity. So that is a plastic section, plastic resistance. That is Fy into BD square by 4. So in between some section it reaches to the full elastic section capacity, Fy into BD square by 4. Are understood? So now, so this is the elastic section capacity. This is the elastic section capacity. It is a full plastic section capacity. In reality, we only not consider. In reality, if you general take its elastic design, in center we have to take only Fy into Z. Fy into BD square by 4. See, BD square by 6 only we have taken it. This is the design, elastic section design. Okay, in reality. But now it is a plastic design. So plastic section capacity you have to analyze it. Okay, now you can see it is the distance between these length. This length is called plastic hinge length. Plastic hinge length. Sir, what is that, sir? So it says, just to see it is, this section reaches to the elastic section full capacity. Elastic section. This section also reaches the elastic section and means Fy is reaching at the outermost. Later remaining every section enters into the plastic zone. Later every section enters into the plastic zone. This section is reaches to somewhere in between. This section is fully reached total plastic section capacity of that section. But this section is somewhere, some zone, some part is reaching to the plastic, some part is reaching to the enters into the plastic zone, some part is into the elastic section. Okay, are understood? Otherwise we already did it in somewhere. Where it is? It is in this second class you already see it. This is a fully elastic section, only elastic analysis. This is fully plastic. This is some part is in elastic, some part is in plastic zone. Are understood? So we calculated that capacity also, that capacities. Okay, so same thing. So this section reaches to the elastic capacity, and the same meaning you can understand. This section doesn't give the full elastic capacity also, because there is no loading on that. There is no loading on that section. That's why it gives some part only. Okay, so same thing. Now you can understand, this section gives the full elastic section capacity. This section full gives the full elastic capacity. This section full gives the fully plastic capacity. So in somewhere it reaches to some part is in elastic, some part is in plastic, some part is in elastic. So that's why this length is called a plastic hinge length. Plastic hinge length. Okay, so what is that length? What is that length? If so that is the question, that is the called questions. Find the length of the plastic hinge if the section is rectangular when point load is applied at center? That is the question. Then you can find it. Can you find it? Easily find out here. So very simple. Okay, very simple. This is Fy into Bd square by 6. This is Fy into Bd square by 6. So this value is Fy into Bd square by 4. So find out this length. Find out this length. So this length is what? This length is L by 2. This length is L by 2. Understood? This length is L by 2. So you can easily find out. Can you find out? Can you find out? So try it. Try it. It's a 0. So find out. So for 0 to L by 2, it reaches to Bd square by 4. No need of Fy. So okay. For 0 to some length, I don't know. Bd square by 6. What is that length? What is that length? For L by 2, it's for it. So how can you find out this length? So this length, you have to find out this length. Find out this length. Can you find out? So easily find out. So L by 2 into Bd square by 6 Fy divided by Bd square by 4 Fy. Fy cancel. Bd square is cancelled. So L by 2 4 divided by 6. 2 2s are 3s are. L 2 by 3. L 2 by 3. It's not possible. So it's L by 2 4 by 6 2 2s are 2 3. L by 3. So okay. It's L by 3. L by 3. So this is L by 3. So same thing. This is also L by 3. So what is this length? Now you can find out this length. Or is what? What is this length? This length is also L by 3. That's it. If it is L3, it is L by 3. It is also L by 3. So that is a plastic length. Hinge length is L by 3 length. So in center L3rd portion, 1/3 portion enters into the plastic zone. Enters into the plastic zone. Plastic zone means what? We already discussed where it is. So this zone. So once it reaches finally it reaches this point. This is elastic limit. Somewhere here it means plastic zone. It's a plastic zone. It is called total plastic zone. Are understood? We discussed the plastic zone. So that way that is called plastic hinge length. Got the idea? That is called plastic hinge length. Okay, that's it. So you can find out everything. So next problem the same thing, same problem. If the beam is loading by a uniformly distributed load. Uniformly distributed load. Can you find out? If the section is loading by a uniformly distributed load. So what is the bending moment diagram? What is the bending moment diagram? This is the bending moment diagram. Are understood? So 0. So bending moment diagram this is the. So no need of what is the loading bending moment. No. So at the failure, this section got the highest moment is applied. So it gives the full resistance at failure. So what is that? This value is already Fy Bd square by 4. Same rectangular section. I am asking same rectangular section. Okay. So what is the plastic hinge length? Somewhere here, I don't know. Somewhere here it reaches to the Fy Bd square by 6. F by BD square by 6. So find out this length. Find out this length. Can you find out? It's a parabolic, na? It's a parabolic. Understood? It's a parabolic. So parabolic transformation. So what is this length? Find out this length. First you have to find out this length. Find out this length. We already know it. What you know it? We already know it. X square by y is constant. Otherwise y is equal to 1 by 4h into L square into L minus x. You already know it, these formulas. We have to use it. So what you use it? So we use this. I think that is a better idea. So we already discussed that formula previously. So now I will see. So for this formula we have to use it. This is the center point. I already discussed. Remember it. This is the y. This is the y. This is the y. Understood? We already discussed x square by y is constant. So now we can see. So now we can see we have to find out this length. Okay, this length. So okay. So see it. For taken this is the center. See for this see. For L by 2 length, okay, L by 2 square, for L by 2 square, it reaches to the Fy BD square by 4, y, L by square. For this length, what is this length? For this length, we don't know, no? For this length, so secant plus c, just observe it here. For L by 2, it reaches to the Fy BD square by 4. For this length, I call it as some x. For x length, it reaches to the Fy BD square by 6. How that is length? But not f by. So what is that reaches? It reaches to this value or this value. Understand? So what is that value? That value is, just observe it. This value. That value is Fy BD square by 4 minus Fy BD square by 6. This is I think I already said. Okay, those things. Okay, so find out it. So can you find out? So easily find out. See, just see, for x square by L by 2 whole square, you can write it as Fy BD square by 4 minus Fy BD square by 6 divided by Fy BD square by 4. So okay, so everything is cancelled. 1 by 4 minus 1 by 6 divided by 1 by 4. Okay, so what is x? X square is, so 4 minus 6 minus 4 is 2. 2 by 4, 1 by 4. So it's 2. 2 minus 4 by 6, it's a 1 by 4. It's a cancel. Multiply with L by 2 whole square. What is that value? Our value 1 by 3rd L by 2 whole square. So what is x? What is x? X is L by 2 root 3. That's it, na? That's it. So this is x by, okay, this is what is that value? L by 2 root 3. So same thing, this is also L by 2 root 3. So we want the plastic hinge length is this is the plastic hinge length. That is the plastic hinge length. So what is that value? What is that value? So I taken first this value. What is that value? That value is L by 2 minus L by 2 root 3. So this is also same. So now I conclude that plastic hinge length is L by 2 minus L by 2 root 3 multiply with 2, because this and this. Okay, what is that value? That value is, you can just multiply with and cancel it. You will get it what? 2 root 3 minus 2 divided by 2 root 3 multiply with 2 cancel. So that value is 2 root 3 minus 2 divided by 2 root 3 of L. Just find out this value. This value is 0.422 L. Just find out it. That's it. That is the plastic hinge length when the uniformly distributed load is active. Got the idea? That's it. That's it. So that's it now. So somewhere some of the problems they asked in terms of the shape factors. In terms of the shape factor, they ask shape factor means what? Zp by Z. Are understood? So no need of calculating these values. No need of knowing these values. Just no required of these values. Just find out the in terms of the plastic hinge. See, in terms of the shape factors. So because some of the sections you don't know the exactly what is the section capacity. What is the capacity of plastic section, or what is the capacity of elastic section. So at that situations you don't need at all. Okay, so now if you see same problem, if the same problem someone asks in terms of this shape factor, in terms of the shape factor, if you ask it, so what you do? So just see, it is just same problem. This is MP, this is My, yield capacity. This is MP, this is My. So exactly length is same. This is the length. Okay, if someone asks in terms of the shape factor, because we already find out the shape factors now. We already find out different shape factors. Where it is? Different sections shape factors. We calculated it now. Somewhere we calculated so many shape factors. Where it is? This is a rectangular section. So see, this is a circular section. What is shape factor value? We already know its shape factor value. This shape factor is in the same. This shape factor you can calculate it. You can find out it. We already find out what is the plastic section, plastic neutral axis. So you can find out whether you will get this value or not. This is also you can check it is. These are all shape factor values. That's why someone insists to calculate in terms of the shape factor value. So how can you do? Is see, this is MP, this is My. So same what we did this thing. See, once again I will do. This is MP, this is My. Are understood? So I already said this is X, this is L by 2. But if you taken this is the center, you will get this value only. X square by Y. X square by Y is constant. So this is this you will get it. Are understood? This is this curve. This curve is suitable for X square by Y is constant. Parabolic. So we already write down like this. Same thing for X. For X square is what? MP minus My. Are understood? For X square it is what? Y. Y is this value. Are understood? Y is MP by My. Are understood? So for Y, for L by 2, for L by 2 is MP. For L by 2 is what? For L by 2 is MP. Got the idea? Got. So now you can see it is where it is. What is this? This. Okay, now you can see. Now you can write down x square by L by 2 whole square is mp minus my by mp. Understood? So what is x square? mp minus my by mp multiply with L by 2 whole square. So you can subtract, not subtract, mp by mp is 1, my by mp into L by 2 whole square. Okay, so what is that value? My by mp is what? My by mp is what? Fy into z. This is my into zp. So this is what? Z by zp is what? 1 by shape factor. That's it now. So that is 1 by shape factor multiply with L by 2 whole square. That's it. That's it. You can write up. So what is x? X is L by 2 root of 1 by 1 by shape factor. Got the idea? Got the idea? That's it. That is exactly the idea. So okay, that is exactly the idea. Okay, that's it. That's it. You can find out this x. Okay, so same problem I will ask another very simple problem, for a simple problem. So if a overhanging cheek, so cantilever beam is there. Cantilever beam. Find out the plastic hinge length when the load is applied at edge. At edge. So you already know what is the bending moment diagram. This is the bending moment diagram. That is not. So first it reaches to the MP. Somewhere it reaches to the my. So again it is a rectangular section. So no need of rectangular or anything. So just is MP my. Okay. So later if you know this value, you can find out, you can insert the shear shape factor value for rectangular section. It's some, so 1.5. For circular section it has some value. So first the plastic hinge length find out in terms of the shape factors. That is useful. So no need of sections. Later you will use that value directly, a shape factor value. Okay, that's it. That is now. So what is this length? We don't know, sir. So this length is L. So same thing for L, it is MP. For his x, my. So if you know this is x, if you know this is x. Okay, so that's it now. So can you find out this value? What is x? X is my into L by mp. So we don't want that length, we want plastic hinge length. This is the plastic hinge length. So, okay, so that is plastic hinge length is L minus my L by mp. That is the plastic hinge length. Plastic hinge length. So now you can find out L minus L, just take out of sample outside. L take out 1 minus my by mp. My by mp means Fy into Z divided by Fy by Zp. That is the Fy is cancelled. Same material, same Fy is there. Z by Zp means that is the shape factor. 1 by shape factor. That is 1 by shape factor. That's it. That's it. Huh? So if you use the rectangular section, if you said some rectangular, if you said rectangular, what is the shape factor? For rectangular, shape factor is 1.5. Just take it as 1.5. 1.5 minus 0.5. What is that value? If it is rectangular, so 1.5 minus 0.5 divided by 1.5. 1 by 3. It's L by 3. If it is give circular, 1 minus 1 by shape factor. What is the shape factor for circular section? We discussed or we derived. So what is the shape factor for rectangular section? It's 1.698. Understood? It's 1.698. So use it 1.698. Find out the value. For any different sections, you can easily find out the plastic hinge length. Got the idea? That's it. That is the plastic hinge length. That is the one topic. Okay, keep aside. So these are all asking GATE regularly. What is the plastic hinge? What is the meaning of plastic hinge? Are understood? So it is what the fibers are the sections. Which sections are entered into the plastic zone? How much portion in the total beam enters into the plastic zone? Got the idea? What is the plastic hinge meaning? We have to understand the meaning, not a problem. So how much portion in the total beam enters into the plastic zone? That is the plastic hinge length. Okay, so that's it. End of the plastic hinge. Now we will find another topic. Next topic is moment carrying capacity of the, not a section, it's a beam, or you can call it as maximum load we can applied on the beam or structure. So that is the topic. Maximum load that can applied on the section, or not a section, on the structure. So how much load the beam can withstand? That is the topic now. Okay, so you can call it no need of calculating moment carrying capacity. This is a full-time subject in RCC and steel structures. That's why we can avoid this line. But this is also same meaning. How much load it can take in, that is also same, no? So see it is. So now you can see that is the topic now. So how can we enter into the topic is just listen. So this is also called calculation of collapse load. Calculation of the collapse load. Understood how much load it means? Also calculation of the collapse load. Okay. For this, every structures maintain three basic rules. What is that rule? At any situation, equilibrium is satisfied. Equilibrium means what? X is 0, Y is 0, moment is 0. That is the equilibrium. So there is no movement in X direction, Y direction, and rotationally. There is no movement at all. So compulsory it will satisfy the equilibrium. And it yield conditions. Yield condition means the fiber must reach the yield point. The fiber must reach the yield point. Are understood? Must crosses the yield point. And also you can also call the fiber must cross the yield point or yield load. And also the bending moment at any section should not cross the plastic moment of the section. Okay, this is basic. Bending moment at any section should not cross the plastic moment of the section. If it is crosses, that means what? That is a failure. So just edge, we take an answer that bending moment at any section should not cross the plastic moment of the section. The fibers must exceed the yield point line. Okay. So last one is mechanism condition. At collapse, sufficient number of plastic hinges must be developed. So it reaches to the mechanism, then only it failures. Now we already discussed. Okay. At collapse, sufficient number of plastic hinges must be developed. Sir, what is the sufficient number, sir? We already discussed there how many number of plastic hinges are required to the basic structure into the collapse, basic structure into a mechanism. We discussed now. So that means at failure, okay, collapse load. What we have to find out? Calculation of the collapse load. At failure, mechanism is satisfied. For mechanism means if it is reaches to the mechanism, the structure must be raised or sufficient number of plastic hinges must be developed. Understood? If it is not developed, that is not entered into the mechanism. We have to calculate the collapse load of the system based on the mechanism. So how we can find out? We can see it is. But sufficient number of plastic hinges must be developed. Okay. Equilibrium is satisfied at everywhere. Yield condition should be satisfied. So the fibers must be cross the yield points and bending moment in any section should not cross the plastic moment. If these three basic parameters are satisfied, we have now another two theorems are there. Lower bound theorem, upper bound theorem. So this is called a static theorem. Okay. So second is upper bound theorem. It is a kinematic theorem. Sir, what is this two? I will explain. Okay. What is these two? What is the static theorem? What is the kinematic theorem? Okay. I will give. Okay. So first we will go with lower bound theorem. Lower bound theorem. There is nothing much is there here. Very simple. Okay. What he said is a load determined on the basis of any assumed collapse bending moment diagram in which the moment at any section is less than the plastic moment. A load determined on the basis of any assumed collapsed bending moment diagram in which the moment at any section is less than the plastic moment is less than or equal to the collapse load. Is less than or equal to the collapse load. So what is that meaning, sir? A load determined on the basis of any assumed collapse bending moment diagram in which the moment at any section is less than the plastic moment is less than or equal to the collapse load. So that means called this less than. It less than is called is lower bound theorem. Sir, what is that, sir? What is that meaning? I will explain only this. Later next class. So what is that meaning? If you see, it is it must be satisfied equilibrium and yield condition. No need at all. So see, it is just see, it is very simple. What is that meaning? Sir, if a structure is there, simply supported, load is applied at W. So what is the bending moment? Bending moment is this, sir. WL by 4. We have to find out the collapse load. Collapse load. Where when the system is collapsed, when that load reaches exactly the W reaches some point, the system is collapsed. Okay. See, now we see the load determined on the basis of any assumed collapse bending moment diagram, in which the moment at any section is less than the plastic moment capacity. See, this is exactly load is increasing, just touching. If you see, just touching the capacity, final plastic moment capacity. If the load is increasing, W is increasing. If W is increasing, the load means this is the bending moment on that section is increasing. Are understood? The section, that is a WL by 4. W is increasing. Okay. So when it is failed, the failure is happening. This reaches to the MP. Are understood? This reaches that section. The section capacity of this section. If you taken this is the section. The section capacity is MP. The load on that section reaches to the MP. It is collapsed. That means you can just assume that MP is equal to the WL by 4. So W is what? What is W? W is 4 MP by L. If the W is reaching that point, the section is reaching the MP. The section reaches to collapse. Sir, what he said, sir, compulsory we have to develop where it is. We have to develop sufficient number of plastic hinges, sir. So that's it. So if the section is reaching to the MP, that means what? This point is what? The hinge. Understood? This pointed giving the whole strength MP. So the section now turns into the plastic hinge. The section turns to the plastic hinge. Okay, are understood? The section turns into the plastic hinge. So one plastic hinge is formed. It enters into the mechanism state. So sufficient number of hinges are formed. One hinge is formed. Compulsory MP should be reached. So what is the W? The W is 4 MP by L. If the 4 MP by L, this W is 4 MP by L. This section, the load is MP. The load is MP. The section capacity is also MP. The section is turns into the mechanism, or section gives the whole strength. Section turns into the plastic hinge. It is a collapse. Got the idea? That's it. But that's a very simple. Got the idea? So what is the collapse load? That collapse load is 4 MP by L. So now you can see, once again you can assume that, see, a load determined on the basis of any assumed collapse bending moment diagram. This is a bending moment diagram, in which the moment at any section is less than the plastic moment. At any section is less than the plastic moment, sir. Less than, sir, is just reaching. This is the point of this. We are at just left side, not right side. Just left side. Just enters. It is increasing, just enters. So that's why these basic rules are formed. Basics, how the load is distributed is exactly follow our basic structural rules before the collapse. Just before the collapse, it follows everything. So that is the one. We are in left side. Load is increasing. We are just left side, just reaching the plastic moment value. The section just enters the plastic. If it enters the plastic, it is no more. It is unstable. There is no bending moment. There is no bending moment at all. Are understood? If it is a hinge, there is no bending moment at all. Just enters. Just now enters into the hinge, we got that the capacity is MP. So just we are at left side. That is called lower bound. That is called lower bound theorem. Okay. So based on that, you can find out the W is 4 MP by L. If you apply that 4 MP by L on that load on the system at center, the system is collapsed. Sufficient number of hinges are also formed. The system enters into the collapse system. Okay. Sir, it is very simple. Is it okay? Yes, it is okay. We will see the next. What is upper bound theorem? We will different structures, different loadings, and we will do it. Okay. That's it. Today's class.